So, in the last lecture we looked at this slide where we compared the changes in Antarctic and Greenland, which is in Arctic, and we noticed that the temperature changes which are deduced from the changes in the oxygen 18 isotope are much more in Greenland than in the Antarctic. And the question is, of course, that's because the northern hemisphere is land, southern hemisphere is mostly ocean. So, changes in the northern and southern hemisphere will not be identical. Okay? But still you notice that certain warming events are coincident, but in many other cases they go in the opposite direction. For example, here it is same, the cooling here is same as cooling here, okay. But you look at let me see, can I show you an event where things are going, yeah, here it is warming, where it is cooling here. So, there are two kinds of phenomena here. For certain climate events, Greenland and Antarctica go together. In others, they go in the opposite direction. Okay. To understand that, we also look at methane. Methane is a greenhouse gas which is also measured in the ice core. For example, in this event here, when there was a cooling coming from 85,000 years ago, there was cooling in Antarctic, there was cooling in Greenland, and there was cooling in Antarctic, and the methane declined. Okay. So, the decline of methane triggered a cooling in both hemispheres. Okay. That is because methane is a gas, it is uniformly mixed in the atmosphere, and hence the concentration of the methane both in Greenland in this graph and in Antarctica are similar. Okay. The changes in methane over Antarctica and over Greenland are very similar because methane is uniformly mixed, but surface temperature need not follow in the two hemispheres, because Antarctic responds to temperature in a different way than Arctic, because Antarctic is a land surrounded by ocean. Well, Arctic is an ocean surrounded by land. So, they do respond in a different way as far as temperature is concerned. But in certain events they are similar. In some other events, for example, here this change is similar, but here it is different. Okay. Where methane did not change much, they are different. So, this we have to understand a little bit further. Okay. So, what people have done is they took the simulation of all the abrupt changes that occurred, okay, and they put them together by looking at the sudden warming event, that is the 0 time is the warming event in all these 6 events they are looked at. There are 6 Dansgaard-Oesterreich oscillation events that they studied, and to show how similar they are, they rearrange them with the same timeline starting 200 years before the sudden warming, that is the Boeing-Alaroy kind of event, and subsequent 1000 years. Okay. So, they are looking at how the warming event started and then how it cooled slowly. Okay. And the key message here is that warming event temperature change, okay, it is from around -22 in Greenland to -14. Okay. So, 8 degrees change in temperature occurred in 100 years, which is very rapid. Okay. Remember, right now global mean temperature over the last 100 years about 1 degree. Okay. So, here in Greenland, not global mean, In Greenland, a change of around from minus 22 to minus 14, 8-degree warming occurred in a matter of 100 years. So, this is a very rapid event that occurred in the past. Okay? So, one cannot rule that out in the future. So, this point we will come up when we talk about impact of climate change, that although it has warmed only 1.5 degree in the past 150 years, one cannot rule out much faster change in temperature in the future as CO2 goes on increasing, because it has happened in the past. Okay? And but what is interesting is, although the warming was very similar in all these 6 events, the cooling was not. The cooling shows a lot of difference. Okay? So, that is the message from this slide, that the warming events are very similar, probably triggered by increasing greenhouse gases, but the cooling event, the next 1000 years, the cooling occur at different rates. Okay? So, cooling depends on many more factors other than greenhouse gases, and they do not show the same trend. Some of them cool slowly, some of them cool rapidly. So, there are many more factors that come into play when you look at the cooling events. Okay. Now, in order to understand some of these features, you have to understand what happened in North America. In the North America, during the last ice age, there was a huge ice sheet called the Laurentide ice sheet, covered almost most of Canada. Okay? That ice sheet was this big, up to this size, and then it started melting rapidly around 20,000 years ago. And when this figure has been drawn, it had retreated, the ice had retreated from here to here. Okay? When the ice retreats, you have water that is there behind the ice sheet. Okay? So, a lake forms. Even now it is happening in the Himalayas. As the ice melts, lake forms behind the ice, and here is that lake which was there, and one of those lakes is very famous, called Lake Agassiz, named after a famous geologist who was one of the first people to propose that there were lots of ice ages. Okay? So, this Lake Agassiz was a huge lake containing a lot of ice melted water. Okay? Now, when this Lake Agassiz grew and broke through all the ice sheet, it discharged into the Atlantic Ocean. This was a major event which occurred in the Atlantic, when Lake Agassiz could break through the ice sheets and start discharging into the Atlantic Ocean. This was one of the meltwater pulses, when this huge amount of water which was trapped behind the Laurentide ice sheet came out. It caused a very large rise in sea level in a very short time. Okay? And that is what we will be looking at. Okay? So, the retreat of the Laurentide ice sheet allowed Lake Agassiz to drain eastward into the Atlantic Ocean. The famous oceanographer Wallace Broecker postulated almost 60 years ago that large amount of fresh water were discharged into the North Atlantic about 12,900 years ago. Okay? Broecker and George Denton proposed that this large influx of fresh water may have stopped the higher density seawater in the North Atlantic from descending into lower depths. Okay? So, their argument is a large amount of fresh water coming in would have reduced the salinity of this top layer, and so the density goes down. If the density is lower, it cannot sink. Okay? thereby interrupting the thermohaline circulation. The thermohaline circulation demands that the water near Greenland should lose heat, become cold and start descending. But if a lot of fresh water is added from Lake Agassiz, this water will not be dense enough to sink, because fresh water reduces the salinity and the density. And so the temperatures were relatively low prior to Younger Dryas in Antarctic and rose during Younger Dryas, and this warming of the Antarctic was on account of deceleration of the MOC. So they are arguing that when MOAC decelerated, Antarctic warmed. Why did Antarctic warm? Because normally when AMOC is strong, it is transferring heat from Antarctic to Arctic. Okay? The Arctic remains at constant temperature. But when this movement of water from Antarctic to Arctic stops, because AMOC is stopped, then heat is not transported from Antarctic. So Antarctic will start warming up, okay, because you are not losing heat to the Arctic. So if thermohaline circulation slows down, less heat would be transported from South Atlantic to North Atlantic, and this would cause South Atlantic to warm and North Atlantic to cool, and this pattern is called bipolar seesaw. That is, the changes in the northern and southern hemisphere Atlantic are different. So as the circulation weakens, less heat is transported to the northern hemisphere. So southern hemisphere warms while the northern hemisphere cools. Okay. Now this bipolar seesaw was simulated by Stoiker and Johnson in 2003. Okay. So this bipolar seesaw involves the southern Atlantic to cool while northern Atlantic is warming. Okay. And you can write down the rate of change of temperature as the change in temperature in north and south, and the rate of change is given here. Okay. Now this is a simple equation, linear equation. You can integrate that using Laplace transform, and you see that the present temperature of the Atlantic is dependent upon the North Atlantic temperature before so this Tn of T1 T prime tells you what is the temperature in the period before the time t, and that affects the integral. So integral is a contribution of temperature of the northern Atlantic, not the present but in the past. Okay. This is of course the surface temperature decay. So there is a decay of surface temperature and also decay of the present temperature. Now this term is the integral term, is complicated to understand. The direct term which shows how temperature will decay in response to southern warming of the Antarctic. Now the bipolar seesaw with a certain heat reservoirs causes this bipolar seesaw. So you have a lot of heat stored in the southern hemisphere, and as North Atlantic oscillation builds up, it shifts the heat from south to the north. So that's the point. And here is again a long time series of data from Greenland and Antarctica. Antarctica is shown in green, Greenland is shown in blue. Okay. And for this simulation, Stocker and Johnson assume that the time scale is around 1100 years. Okay. Time constant they used in their model. Now, what they are showing is that the abrupt Dansgaard-Oeschger oscillation in the north is clearly seen in the simulation, okay, and is similar to what is there in Antarctic. Okay. So, what they are saying is that their model for assumed time constant to be around 1100 years is able to reproduce the major warm events which occur in the northern hemisphere, of course also occur in southern hemisphere, and they are able to show that they are able to simulate it. So, this gives us some confidence that although the models are fairly approximate, still they do carry enough information about how the Atlantic Ocean will respond to increase in CO2. Now, another interesting result they got from this simulation, they show that the rate of change of surface temperature decays rapidly, and they expand this in a Taylor series and get the leading term, which goes as delta T by 2 tau, where tau is the time constant, times T. And when they plot the duration of the event with actual delta T, it goes along a linear line. This is remarkable. So, this approximation they are making is they are taking the first term, and the second term is the Taylor expansion for small time. So, ds by dt at time t into t, and if you assume that, then change in temperature in the Antarctic should be linearly proportional to the duration of the warming, okay, of the Greenland stadial, that is the cool period. Okay. So, to me this is a very nice proof of the simple model, because it shows that how much temperature rise will occur is related to the duration of the Greenland stadial, that is a short glacial period. Okay. So, this to me is a good show that the simple model that they developed, of the bipolar seesaw between southern and northern hemisphere is quite good, because it shows a very good correlation with about 10 DO events. So, the total warming of the DO events is related to the duration of the Greenland stadial as found in the EPICA ice core from Greenland. So, to me this shows the value of simple models. Although simple models make many approximations, so you must be somewhat suspicious, but they are useful to make such predictions which can be verified against observations, and with the agree our confidence in these model increases. Now, here is another simulation done by Stocker and Schmittner, okay, and using a somewhat simpler model, not the full complete model, called the Bern 2.5 dimension model. So, to predict the evolution of the meridional overturning circle, AMOC, okay, during a warming scenario. Okay. In this scenario, they show an increase in carbon dioxide, various increases they have artificially put in various kinds of warming, fast warming, slow warming, and fast warming and then remaining constant, slow warming. In this case, warming occurred in 50 years, the increase in CO2 occurred in 50 years, here the increase in CO2 occurred in 200 years, then remained constant. Okay? And the rate of increase CO2 was not the same in all these. Okay? And then you look at the maximum overturning circulation because of this warming, okay, increase in CO2, the circulation weakens, which is what you remember that we are all worried about the fact that CO2 is increasing now from 280 to 420 already and will continue to increase the next 80 years. How fast will AMOC decline? Because the decline has serious consequences, which we will talk about later in this course. So, this shows that because of this warming introduced in this simulation, AMOC declines over a 150-year period, okay, gradually. But there are cases where it totally shuts down. This green line, which corresponds to this green, the fast change, that is increase in CO2 by around 450 ppm in about 50 years, which is a very fast change, it almost goes to 0. Okay? And so, what this simulation shows you, it warns you that any rapid increase in CO2 in 100 years will have a serious consequence. So, this is an important message for policymakers, because if we continue to burn fossil fuels the way we are doing now, we may get a couple of 100 ppm change in 100 years. It is quite possible. Okay? So, at the age of 2 to 3 ppm per year, over 100 years you will get change of 200 300 ppm, which is comparable to what they have done here, and then the AMOC will decline rapidly and may come to a stop in about 200 years. So, this simulation is a clear warning that a rapid increase in CO2 can lead to a shutdown of the AMOC. So, this has again created a lot of discussion and warning among scientists and policymakers that a rapid increase in CO2 is not safe. Okay? So, abrupt climate change may not have been a merely feature of the past, but may be induced by the buildup of CO2 in the atmosphere. Coupled model studies have shown that global warming can lead to a collapse of the North Atlantic thermohaline circulation. So, this is a question that is of great concern for everybody, because the North Atlantic meridional ocean circulation is beginning to decline, and higher atmospheric temperatures and generally wetter atmosphere and increased moisture transport from low to high altitude will lead to increased precipitation in the North Atlantic, okay, and reduced surface salinity and density, interrupting the deep convection and bringing the Atlantic thermohaline to a halt. So, that is the concern now, that the world is warming rapidly and moisture is increasing, and that may trigger a collapse of the Atlantic meridional ocean circulation. As a consequence of this collapse of the Atlantic meridional circulation, northern Europe might cool even under global warming. This is a very interesting result. Right now Europe is warming rapidly, but if the AMOC stops, it starts cooling rapidly, and thus making, I think I lost this, thus leads to abrupt change in the climate of the European continent. Okay? So, what Stephen Rahmstorf, a well-known expert on this AMOC, has said, the risk of AMOC tipping as a global warming continues should be taken very seriously, considering the devastating consequence of such an event. On the basis of a whole series of new studies in the last 10 years, the risk already appears to be significantly greater in this century than what we had assumed in the past. So Stephen Armstrong said recently that the last report of the IPCC may have been too conservative. They thought that the chances of AMOC halting, collapsing was very low, maybe 10%. But today, based on more recent simulation and more data, it looks like it may not be 10%, maybe much higher. If that's the case, it calls for a major change in the way we plan to decarbonize the world. So this calls for a rapid decarbonization, which was agreed upon during the last Paris Agreement in 2015. But nothing much has happened so far. After 2015, many countries made promises to rapidly reduce their CO2 emission, but nothing much has happened because the Paris Agreement is not a binding agreement. It is a voluntary agreement of all the countries. Those countries have not kept their word. And the countries have been distracted by other events occurring in the world, and so action has been taken, and Stephen Armstrong is warning that this may have a serious consequence. Now let's look at the actual data. Okay, this is from the book Global Warming Science by Eli Zipperman, and it shows that between 2004 to 2020 there have been decline in the AMOs, a substantial decline, but it recovered. So based on these 16 years of data, one may be complacent and assume that this variation between 25 Sverdrups and 5 Sverdrup is a part of the natural oscillation of the AMOC. Okay? So for a long time people said, all right, it goes up and down, this is to be expected for natural climate variation. But the recent work that I have shown you warn you that this may be not the right conclusion to make. Based on just 16 years data, you cannot make any categorical statement about what could happen in the next 100 years. Okay? So this is a warning. Now, if you look at model simulation, they are showing a decline from around 25 Sverdrups now all the way to 10 Sverdrups is almost collapsing by 2100 if we followed the what is known as RCB 8.5. This is the business as usual. That is, you continue to burn fossil fuels at the same rate we are doing now, and so the CO2 will increase by 2 to 4 ppm per year. And if we do that, this model clearly shows that there will be a decline of the AMOC, and by 2100 it will almost collapse. So to me, this is a clear warning coming out from model simulations that we cannot afford to go in the present rate at which we are burning fossil fuels. We have to make very, very drastic changes to our economic system to cut down on fossil fuel emissions and move to solar and wind and other renewable energy sources, so that this drastic decline in the AMOC does not occur. Okay? So that was a part of this lecture to warn you that AMOC decline is a real possibility. Now, in the next lecture, I will talk about how the Earth came out of the last interglacial 20,000 years ago to the present. And there one of the mysteries was we saw changes in carbon dioxide and changes in temperature going almost together, okay? Because some of the data we had got about 30-40 years ago were not of a high resolution. So we could not show whether the temperature increase occurred first or the CO2 increase occurred first. Which came first is very important, because in the last 50-60 years, both the CO2 increase and temperature increase occurred together, and most scientists believe that the temperature increase which occurred in the last 60 years is triggered by the CO2 increase. But many climate change deniers and skeptics say, no, it may be possible that because temperature went up, the CO2 came out of the ocean and CO2 increased. So they are not convinced. So in the last few years, more accurate data has been obtained, and they show that the increase in CO2 occurred first, and this was followed by an increase in temperature. This is a very important work done about 10 years ago and by Shakun, and which I will discuss in great depth in the next lecture, because this completely removes any doubt about which came first, the CO2 increase or the temperature increase. Till recently, people kept arguing that we don't have to worry because this CO2 increase is caused by increase in temperature, and CO2 is coming out of the ocean and land, and whatever caused temperature increase, if it stops, it will stop. But now the recent data shows that that is not true. So that will be the focus of my next lecture, which is very important to show that the increase in CO2 is the trigger for global warming. Thank you.